Alcohols. Today's discussion is on the topic of alcohol. Now, as you hear the word alcohol, what comes in your mind? Oh, alcohol, the thing which gives you kicks. No, friends, actually, alcohol is not the only thing which is used for consumption, but it has diverse uses, and we have thousands of kinds of alcohol which have different kind of uses in industry as well as in synthetic chemistry. So, today's topic is alcohol, and we are going to discuss about that what actually are alcohols, how they are classified, how the nomenclature is given to them. We will also discuss the preparation of alcohol by reduction, and then we will discuss the preparation of alcohol by other methods. What are alcohols? As you can see here, compounds with general formula ROH, where R is an alkyl group or it can be a substituted alkyl group, are called alcohol. The simplest and most common alcohol, which I think all of you know, is ethyl alcohol. We will now classify alcohols. The most easiest way to classify them in three categories: the primary alcohol, the secondary alcohol, and the tertiary alcohol. The basis of classification of alcohol is the type of carbon to which the hydroxy group is attached. As you can see from the examples here, a primary alcohol is one in which hydroxy group is attached to a carbon having two hydrogens. In case of secondary alcohol, you can see that the hydroxy group is attached to a carbon having only one hydrogen, and in case of tertiary alcohol, here you can see that the carbon is attached to three alkyl groups which can be similar or which can be different also. Here you can see, in case of benzyl alcohol, the hydroxy group is attached to phenyl ring via CH2 or methylene group. So, this kind of compounds are called alcohol because the hydroxy group is not directly attached to the phenyl ring. But here in this case, you can see that the hydroxy group is directly attached to phenyl ring, and that is why the name given to this kind of compound is phenol. We will now discuss the nomenclature of alcohols. Alcohols, you see, are the alkyl derivatives of water. If you replace a hydrogen of water by an alkyl group, alcohol results. In case of IUPAC nomenclature of alcohols, the root word is alkane, from which E is deleted and a suffix OL is added, which results into the name of the parent or the resultant alcohol. In case of ethanol, you can see that if I delete E from ethane and add OL, it becomes ethanol, or we can say a 2-carbon alcohol is named as ethanol. Similarly, a 3-carbon alkane is propane. Deleting E from that and adding OL into it, it becomes propanol. So, a 3-carbon alkane is named as propanol. We will now discuss some rules for naming alcohols. First rule for naming alcohols is the longest possible continuous carbon chain with hydroxy group is chosen. The second rule is the position of hydroxy group in the parent chain is assigned lowest possible number. The third rule is that the position of other groups or substituents to the chain is then chosen using lowest possible numbers. The hydroxy groups take priority over double and triple bond. We will now discuss the rules of nomenclature with the help of some examples. Here is a compound in which we can number the molecule either from the side of carbon having hydroxy group or from this side or from that side. If we started from here, then the hydroxy group will take position 5, and similarly if we start from here, then also it is going to be position 5. but we have to give minimum possible number to the carbon having hydroxy group. That is why the numbering in the molecule, or we can say the longest possible carbon chain, is chosen in such a way that minimum number goes to the hydroxy group, and position 4 gets a methyl group. That is why the name 4-methyl 1-pentanol has been assigned to this molecule. In the next example, you can see the numbering of longest possible chain is done so as to give the hydroxy group minimum number, that is 2. That is why the name 5-phenyl 2-hexanol is given to this secondary alcohol. In this example, we have a hydroxy group in the molecule as well as a carbon-carbon double bond. As we have seen earlier, the hydroxy group takes priority over the double bond, so that we have to give minimum number to the hydroxy group and not to the carbon-carbon double bond, and that is why the name of the molecule should be 4-hexene 3-ol and not 2-hexene 4-ol. This again is a secondary alcohol. In the next example, you can see there are many substitutions. We have these two carbons having 3-methyl substitution, this carbon has a normal propyl substitution, and this carbon has a hydroxy substitution. If we number the molecule from here, you can see that the total number of carbon chain comes out to be a 7-member carbon chain, but this carbon chain does not contain a hydroxy group. We cannot choose a carbon chain without hydroxy group for naming an alcohol. What we have to do is that we have to take hydroxy and then maximum possible numbers of carbon in the carbon chain, and that is why the numbering of the molecule is done from this carbon. Position 3 gets a normal propyl group, position 4 and 5 gets 3 methyl groups. That is why the name 4,5,5 trimethyl 3 normal propyl 2-hexanol is the name given to this molecule. In the next example, you can see that one side of the molecule has the hydroxy group and the other side has a triple bond. Again we know that triple bond does not take priority over hydroxy group, so we will number the molecule from this carbon. That is why the name given to the molecule is 2-methyl 4-pentyne 1-ol and not 4-methyl 1-pentyne 5-ol. In this example, you see the hydroxy group is here and we have a carbon-carbon double bond, but the number of longest possible carbon chain here is not with both the groups in the main chain. So what we do is that we take this carbon-carbon double bond or this vinyl group as a substitution over the main chain. The main chain starting from here, the name given to this molecule is 5-ethinyl 2-methyl 3-octanol, or this ethinyl group can also be named as vinyl. In that case, we will say that 2-methyl 5-vinyl 3-octanol is the name of this molecule, but not the name given is 4-ethinyl 7-methyl 6-octanol. Now we will discuss the naming of alcohols or naming of the compounds containing more than one hydroxy groups. Compounds which contain 2, 3 or more hydroxy groups are classified as polyols. The IUPAC suffix diol, triol or tetraol is added after the root word. For example, in this case, this is a 2-carbon diol. 1,2-ethane diol is the name given to this molecule. Here in this molecule you can see that we have 3 carbon atoms, but position 1 and position 2 has the hydroxy group. That is why the name given is 1,2-propane diol. In the third example, all the 3 carbons have a hydroxy substitution. That is why the name given is 1,2,3-propane triol. Here we have some more examples. The cyclohexane ring has 2 hydroxy group or 3 hydroxy group. If it has 2 hydroxy group, the name given is 1,2-cyclohexane diol. In this case, it is a 3 hydroxy group containing cyclohexane, so it is cyclohexane triol. But here numbering is important. If you number the hydroxy from here 1, 2, 3 and 4, 1,2,4 cyclohexane triol will be the name. But if you number it from here, from this hydroxy, the number will be 1, 2, 3 and 4, that is 1,3,4 cyclohexane triol. This is not the right name, because we discussed earlier that the numbering of the substitution is done in such a way that they get minimum number in the main chain. Now we will discuss the industrial preparation of monohydric alcohols. The raw material for the preparation of alcohols in industry are petroleum, natural gas, fats, starch and sugarcane. The methods usually adopted for the preparation of alcohol starting from these raw materials are hydration of alkenes obtained from the cracking of petroleum. Actually, petroleum is a 5 to 10 carbon containing alkane fraction. After cracking, it forms alkenes, and from alkenes, alcohol can be prepared by hydration. The other method for the preparation of alkenes from carbon monoxide and hydrogen is via oxo process. Another method which is used in industry from very long time is by the fermentation of carbohydrates. Then straight chain primary alcohols can also be prepared from polymerization of alkenes by Ziegler-Natta catalyst and followed by the oxidation of the metal alkyls by air. All these methods have been discussed in brief in the subsequent slides. First of all, we will mention here cracking. When a mixture of alkane from gas oil fraction, which contains about 12 carbon alkanes and higher, is heated at a very high temperature, about 500 or more, in presence of variety of catalysts, the molecule break down and rearranges to small, more highly branched alkanes containing 5 to 10 carbon atoms. This process is called cracking. You must have heard this name. Isooctane is 2,2,4-trimethyl pentane. This burns in internal combustion engine very smoothly and has octane rate of 100. This isooctane is prepared by cracking. The oxo process. The alcohols can be prepared from alkenes produced by the cracking of petroleum by oxo process in the presence of octacarbonyl dicobalt catalyst. Alkenes react with carbon monoxide and hydrogen to form aldehyde, and the aldehyde so formed gives alcohol upon reduction with lithium aluminium hydride or sodium borohydride. The next process for the preparation of alcohols industrially is by fermentation. Fermentation of sugar by yeast is one of the oldest processes and is still of enormous importance for the preparation of ethanol and many other alcohols. The source of sugar primarily are molasses from sugarcane, starch from grains. Fermentation process produces 12 to 15% ethanol, concentration of which is done by various distillation processes. We will now tell you some facts about alcohols. Methyl alcohol is also known as wood alcohol and was earlier obtained from destructive distillation of hardwood in absence of air. Ethyl alcohol is also called grain alcohol. Distillation of fermented molasses gives 90% of alcohol, also known as rectified spirit. Rectified spirit further distills to give commercial alcohol, which is a mixture of 95% alcohol and 5% water. Absolute alcohol is dry alcohol obtained from the treatment of commercial alcohol with magnesium. The next method for the preparation of alcohol is by the polymerization of alkenes produced from the cracking of petroleum, followed by the oxidation of metal alkyls. Linear long chain alcohols are prepared by coordination polymerization of ethylene using Ziegler-Natta catalyst, which is titanium trichloride and triethyl aluminum, followed by the oxidation of metal alkyls by air. A variety of alcohols can also be prepared from fats. Fats actually are the glycerol esters of long chain carboxylic acids, which upon saponification form glycerol, which is a trihydric alcohol, and sodium salt of long chain carboxylic acid. The sodium salts of long chain carboxylic acids can be converted into alcohols by the reduction, which we will discuss later on in this presentation. Here now is the flow chart which shows starting from petroleum how we can prepare a variety of alcohol, starting from fats how we can prepare alcohol, similarly from sugarcane or grains we can prepare alcohol. See, petroleum upon cracking forms alkene, which upon hydration gives ethanol. Ethanol, here you can see that petroleum upon cracking giving higher alkenes, and from that we get higher alcohols. This is OXO process for the preparation of alcohol starting from alkenes. Alkenes can be polymerized by Ziegler-Natta catalyst, followed by the oxidation forms higher alcohols. Fats can also produce alcohols, higher alcohols by saponification method. Here sugarcane produces molasses, which upon fermentation gives ethanol. Grains gives starch, which upon fermentation forms ethanol. So, we have summarized all the industrial methods for the preparation of alcohols starting from petroleum or grains, sugarcane, etc. Now, we will discuss the preparation of monohydric alcohols in laboratory. Alcohols can be easily prepared by a number of methods which have already been discussed in the earlier chapters. Like for example, we can prepare alcohols from alkene via addition of water, via addition of concentrated sulfuric acid followed by hydrolysis. We can prepare alcohols by oxymercuration demercuration reaction. We can prepare alcohols by hydroboration oxidation reaction. Alcohols can also be prepared from alkyl halide by nucleophilic substitution reaction, and we can prepare alcohols starting from Grignard reagent. If we treat Grignard reagent with formaldehyde, a primary alcohol is formed. If we treat this alkyl lithium with acetaldehyde, a secondary alcohol is produced. These methods are discussed in relevant chapters in detail. We are not going to discuss them in detail here. We will now discuss the preparation of alcohols via reduction. Alcohols can be prepared by a wide variety of organic molecules. For example, by the reduction of aldehydes, ketones, carboxylic acids, esters, acid chlorides and anhydride. The commonly used reduction methods are Bovold-Blanc reduction, Meerwin-Pondorf-Verley's reduction and catalytic reduction. The reducing agent normally used for the reduction of these classes of organic compound include zinc and acetic acid, zinc and alkali, sodium amalgam in alcohol, lithium aluminum hydride and sodium borohydride. We will now take up some examples where reduction actually is taking place on these molecules with the help of certain reducing agent. For example, this is the example of Meerwin-Pondorf-Verley's reduction, in which acetone molecule is reduced to 2-propanol. The reducing agent used here is aluminum isopropoxide in presence of isopropanol. In the second case, we are using butanol, an aldehyde which upon reduction forms normal butanol. The reducing agent used here is lithium aluminum hydride followed by acidic hydrolysis. In this example we are taking up, it is 2-methyl propanol which upon reduction with sodium borohydride forms a primary alcohol. Catalytic reduction reduces carbon-carbon double bond along with carbonyl group. Lithium aluminum hydride on the other hand selectively reduces the carbonyl group, leaving behind the double bond intact. For example, in case of alpha beta unsaturated aldehyde, if we reduce it with hydrogen in presence of nickel, or if we reduce by catalytic method, the resultant molecule is normal butanol, that is both the carbonyl group is reduced as well as the double bond is also reduced. But if we reduce the same molecule with lithium aluminum hydride, then only the carbonyl group is reduced to primary hydroxy group, whereas the double bond remains intact. So, the use of a proper reducing agent results in the formation of our choice compound. Here, this is an example of reduction of carboxylic group. Reduction of carboxylic group is very difficult and can only be done by strong reducing agents such as lithium aluminum hydride. Carboxylic group upon reduction followed by hydrolysis forms primary alcohol. Reduction of esters can be done either catalytically using molecular hydrogen or by chemical reduction methods. In either case, the product is 2-alcohol. As you can see, the ester upon reduction is forming 2 alcohols. Reduction of esters require high pressure and elevated temperature conditions. The catalyst used here is a mixture of oxide, also called chromite. Here you can see methyl laurate is an ester which is the ester of a long chain carboxylic acid. This ester upon reduction forms lauryl alcohol along with methyl alcohol. The conditions required for this is copper chromite at 5000 per square inch of pressure and 170 degrees of temperature. So, drastic conditions are utilized for the reduction of esters. In the case of chemical reduction of ester, lithium aluminum hydride or sodium borohydride, either of the two can be used. Here you can see ethyl palmitate upon reduction with lithium aluminum hydride forms this 1-hexadecanol along with ethyl alcohol. Functional derivatives of carboxylic acids such as acid chloride and anhydride also form alcohol when reduced with lithium aluminum hydride. Here it is acid chloride, propanoyl chloride actually, which upon reduction with lithium aluminum hydride followed by hydrolysis forms normal propanol. This is propanoyl anhydride. Upon reduction with lithium and aluminum hydride, it forms propanol. Sodium borohydride is a less powerful reducing agent and can reduce aldehydes and ketones, but it cannot reduce carboxylic acids and their derivatives. As you can see here, carboxylic acids and their derivatives, that is esters, acid chloride, anhydride, etc., can be reduced only by lithium aluminum hydride, whereas aldehyde and ketones can be reduced both by lithium aluminum hydride as well as by sodium borohydride. Higher alcohols can also be prepared by aldol condensation of aldehyde and ketones followed by catalytic reduction. Aldehyde, a 2-carbon aldehyde, when treated with concentrated sodium hydroxide, undergoes aldol condensation and forms alpha beta unsaturated aldehyde. This, upon reduction, catalytic reduction, produces a saturated primary alcohol. If we want to prepare unsaturated alcohol, we can use lithium aluminum hydride also, the method which we have already discussed, and apart from that there is one more reagent which can be selectively used. We call these reagents chemoselective reagents, and this reagent can selectively reduce the carbonyl group but not the carbon-carbon double bond. This reagent is called 9-BBN. It is a hydroborane derivative 9-BBN. We will now discuss a very interesting point here, the reduction in nature. The coenzyme NADH, nicotinamide adenine dinucleotide, is obtained from soya bean and has a split personality. NADH is a reducing agent and acts as electron donor in various metabolic processes. NAD plus is an oxidizing agent, on the contrary, in citric acid cycle. Nature uses NADH and NAD plus to interconvert ethanol and ethanol by the use of alcohol dehydrogenase enzyme. We will now summarize the topics which we have so far discussed. First of all, we discussed various classes of alcohols, then the nomenclature of alcohol with the help of some examples. We discussed the industrial methods of preparation of alcohols. We discussed the preparation of primary alcohol with special emphasis on reduction of aldehydes, ketones, carboxylic acids and their derivatives. In the next lecture, we will discuss the properties of alcohols. We will discuss how the hydroxy group in alcohol makes the changes in its properties of solubility in boiling point and in its acidic nature and basic nature.